So, this is a very quick and informal explanation of some of the math behind the Heisenberg Uncertainty Principle. This is not what was actually used to prove it. You can't prove it using this method, at least not as far as I know. There's probably a way to do it, but I'm not going to do it. And essentially, this is just an intuitive proof of it, or an intuitive proof of one of the reasons that it might be the case. So, here's the uncertainty principle itself. The uncertainty in position times the uncertainty in momentum has to be greater than or equal to reduced Planck's constant over 2. For the purposes of this explanation, all we're going to care about is these two things. Uncertainty in position is essentially, when we measure it, do we already know where it's going to be when we measure it? Or rather, before we measure it, do we know where it's going to be? The further spread out the places that it could be are, the more uncertainty we have. So let's say that we have a very simple, oversimplified in fact, waveform of position right here, where the position is along this axis and the amplitude of the waveform, which is related to the probability that we would find it there after we measure it, is along the y-axis. So essentially we have, as you can see, an uncertainty in position of t, because this is positive t over 2, this is negative t over 2, and we can only find it in between there, because everywhere else we have defined to be 0. So essentially, if we have this waveform, and we would never have this waveform because it doesn't happen like this, but if we did, our uncertainty would be t. So, here's the thing. We have two quantities here, position and momentum, and they're interrelated. And they're interrelated in much the same way that if you have just some random sine wave or some random cosine wave, sine wave combination, that frequency is related to the wave itself. And if you want to convert from a time domain of a signal that is, in a sine wave pattern into the frequency domain, if you want to take some weird wave and find the component frequencies, you use the Fourier transform. So what we're going to do is we're going to do math. And I've written math here because when Vladimir explained this to me, he did in fact go through the entire explanation and we did all the math and it was very useful and I don't remember it and the pictures that I took on my phone don't provide nearly enough information for me to be able to reconstruct it, so I've written math. But here's the actual Fourier transform that we do, and what we get out of this is this function. If you don't believe me, you can do it yourself, but this is like what we get. H is the actual amplitude that we're assigning. It's like the probability, but it's not quite. And then we get this sinusoidal expression. And here's the interesting thing about this. If we graph frequency on the horizontal axis and this function of frequency, which is, again, like the probability that we're going to find it at that frequency along the vertical axis, we're going to get something like this. We're going to get something that spikes in the middle and is a decreasing sinusoidal pattern outside. And the interesting thing about that is this. If we have a very large t, which, as you remember, is our delta x, if this letter t is very large, then we're going to get something like this, where the whole pattern is very tight. There's this large spike in the middle. The larger the t, the larger the spike, etc. And so you can see that if we have a waveform like this, we are going to get very little uncertainty in frequency. And of course, frequency is related to wavelength, and wavelength is related to momentum. If you don't believe me, just ask de Broglie. If we get this waveform for frequency, and therefore a similar one for momentum, then you can see we have very little uncertainty because we're pretty sure it's going to be here, and there's very little chance that it could be anywhere else. But even so, the chances are distributed across this very small area. If we have a slightly larger t, we're going to get something like this. We're still pretty sure it's going to be here, and we're pretty sure it's going to be somewhere in here, but we're not completely sure. And there are places outside of here where it could be. And if t is very small indeed, we're going to get something like this, where it is very spread out. And so, you can see that the amount this is spread out is sort of like our uncertainty in momentum, because we're pretty certain that it's going to be here and here alone, or somewhere in this small area. Here we're pretty certain it's going to be somewhere in this larger area, and here, as t approaches 0, the waveform that you get here approaches just a straight line barely above the horizontal axis. This shouldn't be like that. It approaches a straight line just barely above the horizontal axis, and essentially that means that as t decreases, the uncertainty in our momentum increases. Essentially, our t, which is our delta x, and how spread out this is, which is our delta p, are inversely proportional. That explanation was given to me by Vladimir Kremenetsky and Ben Hanel, and it's pretty common. You can find it online if you really look for it, but it's interesting in that it can provide some basis on which you can understand the Heisenberg uncertainty principle.